So in this part, we will do two problems. The first one, D.1, minimum selection problem. Very noisy. Right. Yeah. So this is our first selection problem. Remember, we did a search problem, linear search. And I mentioned there are three basic types of problems we need to do in this class. Search, sort, selection. Search, we did one. Sort, we haven't started. Then selection, the first one today. Okay, all right. Minimum, finding the minimum of an array. Yeah. It's a simple problem. Yeah. Everyone knows how to do it. Yeah. But here, our focus is not on how to find a solution. Our focus is on optimality. Okay? So we use this simple example to learn this optimality question. Yeah. Here. Yeah. It's an important consideration here. All right. So first, let me give you the problem. Our problem number 3. Find the minimum of an array. All right. Given an array with n elements, find the index I such that A of I is the minimum of the array. Simple question, right? Yeah. All right. All right. So here the problem type, selection type. Yeah. So the reference here, I give you, content from these two sections, section 2.3 and 4.5. Yeah. All right. First, let me give you the overall selection problem. Yeah. So this finding the minimum is from 2.3. Okay. This finding minimum. This question. But what part from section 4.5? The selection problem. Okay. Because the whole selection problem we will discuss in section 4.5. Here I just give you the question, but we will not work on the whole selection problem. Yeah. All right, what's the selection problem? Find the kth smallest element in a given array. That's the selection problem. K. Yeah. But the K number should be given. Yeah. As part of an input data, K. When K equals 1, that's the minimum, right? Yeah, minimum. Because the first smallest. Yeah. So this corresponds to a special case. K equals 1. Yeah. K equals n, that's the maximum, right? Yeah, maximum. And the K equals some index in the middle, yeah? Some index in the middle, yeah? The median, for example, median, finding the median, right? Yeah, finding the median. Yeah. Another important selection problem. How to find the median? Yeah. So we will get there, yeah. Finding the median. You can see finding the median much harder than minimum, maximum. Minimum, maximum, the easiest selection problem. Finding the median much harder. All right. Kth smallest here. All right. Then, because the minimum first smallest, very easy. Then later we will learn how to find the second smallest. Then a lot harder. Okay, a lot harder than the first smallest. Yeah, so we will get there. Second smallest. Then third smallest. Much harder. Harder and harder. Okay? So, but then we build up. Okay? Yeah. Second smallest is built on top of first smallest. Third on second smallest, and so on. Okay? Yeah. but not in a straightforward way. Later you will see it's not in a straightforward way. If you do it in a straightforward way, you won't get the best solution. We want to find the best solution, right? Yeah. You won't get the best solution. All right, so let's look at this one first. Yeah. The special case. Yeah. Yeah. Minimum, maximum. Yeah. Let's, do the work. The description of the algorithm, simple, straightforward. Yeah. Here, let me quickly go through the solution first. Yeah. But that's not our main focus. Okay? Yeah. But we need to go through that first. Initialization, when we start, we use a variable called the min variable. We create a min variable to store, because our goal at the end, we want this variable stored the minimum. Yeah. But at the beginning, we initialize this min variable by the value of the first element. So we assign. This is an assignment operation. Okay, we assign the value of the first element to this variable. Assignment operation. All right. After that, then we start our first comparison operation. All right. The general step. We compare this main variable and the value of the current element, current A or Y, that's the current element. So which one is larger, smaller, or equal? Yeah. So here we consider two cases. The minimum, if the minimum is strictly greater than A of I, current element, then its value should be replaced by the current element. That means we find a smaller element to replace the current minimum. Okay, the current minimum can be updated. Yeah. So let's assign A of I to this minimum min variable. Otherwise, we do not need to update, right? Yeah. Otherwise, continue our iterations. Next round, iteration. So compare min and the next element, A of I plus 1. And see if you need to update it or not. Okay? Yeah. Until you reach the end. When you reach the end, whatever element, whatever value is stored, whatever value, because here find the index I, so it may hold, I think it, anyway, index I, anyway, but that index should be returned, anyway, just a little more work, So at the end, the value that is stored in this variable min, that's the minimum value. But then you just, because when you store, so probably you also use another variable, store the index. Just a little more extra work. Okay, a little more extra work. Also return the index if you need it. All right. So that's the solution. Very simple. But next, we want to go to the main point. Main point here. First, you are familiar with the whole algorithm. Whole algorithm is simple as this description. Then we need to start our important discussion. All right. So first, ask a simple question. How many comparisons do we need to find the minimum using this algorithm? Counting. You just give me that number. counting. So here, I only ask you comparison operation. I do not ask you other operations. So you don't count other operations. You only give me the comparison number. Total comparison number. Any quick answer? Because it's not hard. After you go through, can you give me some, Kirill, can you say something? Make a guess. Just make a guess. Correct. And all right. And any other different guess? He said and. Close. It's close. Don't use K. Okay? Yeah. Because K, when it is given, it's fixed. Okay? Don't use that K. Yeah. Really? Some number related to n. Number related to n. Yeah. Yeah. All right. Here, yeah, let me point it out. The correct answer is n minus 1. Okay, yeah, not n. Why? Remember, we go through all n elements, but first one we do assignment, right? First one we do not do. A of 0, there is no comparison here. Okay, no comparison associated with A of 0. Other than A of 0, one element corresponds to one comparison. That's a one-to-one. Okay, one-to-one correspondence excluding the first element. Okay, one element. So here, okay, so we do this. One element corresponds to one comparison excluding, okay, the first element. So when you count, you cannot count the first element. Okay? Other than the first element, there are n minus 1 total elements. So that's why you have n minus 1 comparisons. So here you can see we apply counting by reference another time, right? Yeah. We use elements as our reference objects. Okay? For comparison, it's hard to keep track of, right? Relatively hard to keep track of your comparison. But when we map the comparison to elements, yeah, elements easy to keep track of, right? Yeah. But no first element. Okay? Yeah. Assignment we separate. So assignment we do not treat it as a comparison. Okay? All right. Yeah. So the answer n minus 1. But the next question is important. The next question is it possible we have chance to improve this n minus 1 number? Can we do slightly better than this algorithm? We want to know the answer of this question. Yeah. Yeah. Okay, yeah? Yeah. So here, yeah. So our next step, we need to answer that most important question. Yes. All right. So here. All right. So I already explained. Okay. Yeah. Okay. Yeah. So I do not repeat. All right. Now, is it possible to further improve that question?
Is the array, is it ordered or unordered?
Not ordered. If it's ordered, that's too easy, right? Yeah. If we, yeah. For John's question, if we do not say anything, yeah, we do not say ordered, unordered, then we assume unordered. If it's ordered, because that's a special property, you have to mention it. Okay? You cannot assume it. If we do not mention ordered, then you cannot assume ordered. So that's why we assume unordered. Otherwise, nothing to do, right? It's true. Question?
The most efficient way to find it, lessons, order consideration is the most efficient algorithm.
Yeah. We are working on that. Most efficient, yeah. So because we want to answer that question. Yeah. At this point, we don't know. Okay. Yeah. So look at this one. Is it possible to further improve? Yeah. So we want to see, is it possible we can reduce just the one comparison? Is that how possible? Can we use n-2 comparisons to find the minimum? Yeah. Even just the one comparisons. But if you say no, yeah, you're based on your intuition, right? You're based on your intuition. But can you convince people? Can you use, some very solid arguments to convince people nobody can improve it? Nobody. That's the topic here. That's called optimality of this algorithm. So that's why we want to see if the current algorithm is optimal or not. Optimal, then nobody can improve it. If we can show the optimality of this algorithm, then no, you do not need to do anything because already the best. Don't waste your time, resource on it. It is already the best. Okay? But you need to convince people it's optimal. You need to do a lot of work to convince people it is optimal. Okay? Yeah. So that's why we have this part D of optimality. Two options, we know. Every time when we derive an algorithm, we need to consider these two options. The first one, improve. We want to further improve it. The first reaction. Second, because even if you try very hard, but you couldn't improve. Yeah. That happens frequently. Yeah. Then you may need to think about the algorithm may not be improved. Yeah. In that situation, you need to convince people. Yeah. So the current algorithm is already optimal. Then no need to do any improvement. Yeah. Yeah. Like this one, yeah. Yeah. This one here, I can tell you the answer. It is already optimal. Yeah. But we need to we need to convince people. We need to convince people why it is optimal. Okay? All right. So let's continue. Yeah. Post-solution thinking. We should try to improve solution as much as we can. Yeah. So usually you want to try a little bit. Yeah. Yeah. Only you cannot. Yeah. So you try a few times, but you cannot. Okay? Yeah. So then you want to consider if the current solution has already been optimal. Yeah. But the optimality, in general, to prove the optimality in general, it is very hard. It is very hard in general. All right, so let's look at optimality. Let's understand the harder part about the optimality. Why it is hard. Here I need to explain why it is hard, right? Yeah. Let's try to understand the specific meaning of this optimality. When we say this algorithm is optimal, what's the exact meaning it is? We want to understand that meaning, okay? What's the exact meaning of optimality here? Okay, all right, so let's, yeah. Among all the possible algorithms, we need to show this one is optimal. The question, how can you show it is optimal among all the possible algorithms? Right, yeah, so that's the direct interpretation. The hard part, interpretation, okay? All right, then, how do you understand among all the possible algorithms? Although simple words, right? Simple phrases. What's the exact meaning of all the possible algorithms? Here, we want to understand this phrase. Okay? Yeah. Its meaning looks clear, right? But let's dig a little more. Let us dig a little deeper on its meaning. All the possible. You want to say something, John?
Would it be like all the possible like known?
Yes, good. Known or unknown? Yeah. When you say possible algorithm, do you mean all possible known algorithms or including unknown algorithms? Because there are many algorithms unknown. Do you want to cover the unknown algorithms? Yeah. By logic, because unknown we don't know, right? Yeah. The question, there is a difficulty. When you talk about unknown algorithms, there are a lot of uncertainties, right? Uncertainties. How can you say anything about unknown algorithms, right? Nobody knows. Yeah. But from the logic, you have to cover unknown algorithms. Yeah. Otherwise, how do you claim this is optimal, right? So when you claim one algorithm is optimal, you have to, so here, all possible, you have to cover all the unknown algorithms. Okay? Yeah. Otherwise, your claim is false. Okay? At least it's not convincing, right? If we do not say it's false, at least we can say your claim is not convincing. Okay? Shaky. Shaky. Yeah. All right? Yeah. All right. So that's the understanding. Yeah. All right. Yeah. Including unknown algorithms. Okay? Then, although it's hard, but you have to do it. You have to do it in the right way. We know it's hard. Covering unknown algorithms. You need to take care of the uncertainties from those unknown algorithms. It's hard, but that's the right way, right? No matter it's hard or not, we have to do it in the right way. Yeah. Okay? Yeah. If it's a wrong way, then you're doing some garbage work, right? Yeah. Say something. You want to?
I was gonna ask, is this like leading to the big O?
Oh, no, not there yet. Yeah.
Not yet.
Yeah, that big O module, second module, module number 2. Yeah. Yeah, but here, that big O, yeah. That big O is a rough estimate. Okay, very rough. Here, we are doing very accurate consideration. It's another rough one, okay? Because the big one, you have a lot of room, okay? More or less, But here, even reduce one comparison, it's hard. So our accuracy is even at one comparison. That accurate, okay? Yeah. But big O, never accurate, okay? Big O is an approximation, rough approximation, very rough, okay? Yeah. All right, yeah. Let's continue. This uncertainty covering unknown algorithms. Is it possible? Yeah. The question, you're shaking it. Shaking. Yeah, unknown. Yeah. That's by your intuition, right? Yeah. But let's think twice. Let's think about this question twice. Is it possible to find a way to talk about or to discuss or to characterize unknown algorithms? Cuddy, so nodding, yeah. So you feel it's possible. At least you feel possible. Okay, good. Yeah. All right. Yeah. Well, how? Can you say something? How possible? Yeah, that's hard. How possible? That's hard. Yeah. So let's see. Yeah. Let's see. All right. How to study unknown algorithms. Yeah. At the end, you will know. Okay? At the end, you will know. Yeah. We can study unknown algorithms. Yeah. Yeah. All right? Yeah. All right. So here, let me give you the main idea how to study unknown algorithms. When we say unknown, do we mean we complete, so those algorithms completely unknown? We know nothing about those algorithms? Do we know a little bit? Do we have some information about those algorithms? Is it completely unknown? At least some small portion known. Small portion known, right? Yeah. It's not 100% unknown, right? It's not 100% unknown. Okay? Yeah. There is something known there. All right. So that little information that is known, that can provide us enough information to convince people. So we just work on that little known information. Okay, all right. Let me explain why the answer is yes. We can study because we know something, right? Yeah. Let me say in this way. Let's consider all the possible algorithms that can be used to find the minimum. Okay? Yeah. By comparisons. Yeah. Yeah. That's the known information, right? Yeah. All the possible algorithms that can find the minimum by comparisons. Yeah. So that's our starting point. Yeah. That's the basic information we know. All right? Yeah. How to study unknown algorithms. The key point is this. If we can discover some common property or properties for those algorithms, can we find some common properties? Yeah. Common property here, it means all such algorithms must satisfy this common property. Okay? Even the detail, we don't know the details. But if that algorithm uses comparisons to find the minimum, then it must satisfy the common property. If we can find that common property, then we can use the common property to study optimality, right? Yeah. So let's try to find a common property. Let's explore that common property. Okay, all right. Next, how do we convince people that our algorithm is optimal? This time, we need to dig the common property. Okay? A set of common properties such that all those algorithms that can be used to find minimum using comparisons must have these properties. Okay? Yeah. So we use these properties, then we can make our convincing arguments. All right, so let me do the work here. Okay? So now you closely follow my thinking. Okay? Yeah. So I make a sequence of arguments. Yeah. If you can find any hole, yeah, point it out. Yeah. So we can do some discussion. Yeah. Because I need to do a sequence of deductions, step-by-step deductions. Yeah. So each step, when I make a statement, this statement must be true for all such algorithms. Okay? Common property. That's it. What do we mean, common property? Okay? All right. So let's start that discussion. Yeah. All right. Yeah. But here, to make the arguments, I need to do some mental preparation. Because it's like a mental exercise. Okay, mental preparation. In order to help us understand better, we borrow some real-world experience. We need to borrow some real-world experience. Yeah. And help us understand. Although we don't have to use that, but help us understand better. Yeah. All right. Yeah. So what the experience? Playing sports games. Yeah. Playing sports games. So we use that experience because everyone is familiar with that. Okay, one player plays against another player, one winner, one loser, right? Or tie, things like that. Okay, that kind of experience. And we use the analogy because that activity is similar to a comparison, right? Okay, some similar situation like a comparison. Okay, yeah. One beats another. When we do comparison, also one beats another, right? Yeah. So we use this kind of analogy to help us understand. Yeah. All right. So when we say comparison, so here we can use a match in sports games. Okay. All right. Between two players. Winner, loser. But when we do this kind of analogy, actually there is some difference. Yeah. So there is some difference. Yeah. So it's not completely the same. Yeah. So we know in sports games, a lot of things uncertain. Okay, a lot of things uncertain. Yeah. All right. So for the results, yeah. So we less than. Yeah. So here, yeah, because think about. Our goal, we want to find the minimum, right? Finding the minimum is our goal. That means an element, the smaller its value, the better, right? When the element is smaller, when its value is smaller, then we select it, right? The smaller, the better. So here it's like, if an element has a smaller value, we pick it as the winner, okay? Yeah, because it wins. The final winner, that one has the smallest value. That's the final winner, okay? Yeah. So we use this kind of understanding. Yeah. All right. Equal, tie, greater than, lose. Yeah. All right. Yeah. This kind of analogy, right? Yeah. All right. Then, but there is a key difference. So we need to consider. We need to be aware of a key difference: transitivity property. In our comparison, we have transitivity property, but in sports game there is no transitivity property, right? Yeah. So let me give you the transitivity property in comparison operation. If PA greater than PB and PB greater than PC, then PA is greater than PC. That's the transitivity property, right? Yeah. In algebra. For inequality, yeah, this property must be satisfied. But in sports game, usually it's not satisfied, right? Yeah. Player A beats player B, and player B beats player C. It does not mean player A always better than player C, right? Yeah. Because player C, there is a possibility player C can beat player A, right? Yeah, it's very common. Yeah. 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 So in sports game, that's no transitivity property. You cannot assume transitivity property in sports games. Yeah. So that's a key difference. Yeah. But here, we need to, in our discussion, we need to use transitivity property. No? And it's a common property here. So for all those algorithms unknown, even unknown, this transitivity property must be satisfied, right? Yeah. So we will use this transitivity property to discuss all the unknown algorithms. Okay? Yeah. All right. Yeah. So then, because we have this transitivity property, when we apply this transitivity property of the inequality, we allow some indirect comparison. Indirect comparison. What do you mean indirect comparison? Here, look at it. Player A beats player B. There is a direct comparison, right? Yeah. Player B beats player C. There is a direct comparison, right? Yeah. But we do not need to compare PA and PC, right? Because we already know player A, based on transitivity property, PA must beat PC, right? Yeah. So then we say in this way, PA beats PC by indirect comparison, not direct comparison, okay? Because these players, they do not play directly, they play kind of indirectly, okay? Through player B, then by transitivity, they play by transitivity way, that's an indirect way. That's our understanding, okay? Yeah. So we can do comparisons. We may not do direct comparison, but we do indirect comparison through transitivity, okay? Yeah, that's the meaning. Because in this way, we can save some number of comparisons, right? Otherwise, we'll waste comparison. Because you already know PA greater than PC. Why you want to do a useless comparison? You should not arrange a game between PA and PC, right? Useless. If we adopt that transitivity rule, okay? Yeah. We know in the usual normal sports game, that rule is not, not used. Yeah. But in our context, we need this rule, okay? Transitivity. All right. Now we are ready to make convincing arguments. After this preparation, now we are ready for this convincing argument. All right. Imagine, the final winner, that minimum. That minimum is our final winner. So now we want to find the final winner. That's our goal. Okay. All right. And the final winner needs to beat all the other elements in the array through comparisons, but we allow direct comparison and indirect comparisons, right? Yeah. But you have to, so the final winner has to beat all the remaining elements either by direct comparison, other than direct comparison, by transitivity, the indirect comparisons. Do you agree this statement? The final winner. Otherwise, how do you claim? Yeah. Suppose if your direct comparison, indirect comparison missed one player, one particular player. The direct comparison, you do not cover that player, and through transitivity, indirect comparison, you do not cover that player. How can you claim this main player beats that uncovered player? You cannot claim, right? Because you do not have any information between these two players. Okay? Direct, indirect, no information. Okay? How can you claim this? So here, this statement is true, right? Correct. Yeah. You have to cover directly or indirectly. Yeah. So this statement is correct. Yeah. For all such algorithms. All right. Next statement. If an element loses once, then it is eliminated. Because it cannot be the winner, final winner, right? If an element loses just once, that means it is greater than at least one element, right? Then this element has no chance to be the final winner, the minimum. This statement also correct, right? Yeah. loses. So you're not allowed to lose even once to be the final winner. It's also true, it's common for all such algorithms, right? Yeah, it's common, this statement. Yeah. Shared by all such algorithms. Yeah. Next statement. Each comparison can only eliminate one element. Do you agree with that? Is it possible one comparison can eliminate more than one, two elements? After one comparison, both players are eliminated. Is it possible? No, right? Because there is a winner. How can you say a winner is eliminated, right? Two players play each other, one winner, one loser. How do you convince that winner you're eliminated? Because you win the game, so you're eliminated. How can you do that, right? Question?
What if it's equal?
Yeah. Yeah. Equal, yeah. Let's assume,
That's why it's not.
yeah.
But wouldn't we still use a comparison to see if it was equal or not?
Yeah, but we can modify our operation, okay, to serve our purpose. So that, because if you go back to our original algorithm, when we have an equal case, we include the equal case, right? When we have equal case, we do not replace the value of mean, right? Yeah. So that when there is equal, yeah. How about let's simplify our situation. When there is an equal, we toss the coin. How about that? Just we select a winner and a loser. We have to determine winner and a loser. Let's toss the coin. Okay, we determine winner loser. Yeah. Okay, just get that problem resolved. Okay, in some way, in some fair way, right? Toss the coin, still fair, right? Yeah, in a fair way. Okay, so we do not need to get stuck on that equal case. Okay, yeah. Because in our original algorithm, equal, we have a rule, right? We have a certain rule. Although it's not toss the coin, that means the current winner keeps its title, right? Just like international chess championship. Think about international championship. Yeah, I remember that there is a rule. The challenger, if it's a tie, final tie, the current champion still keeps the title, right? Because the challenger must be the current champion, right? Yeah. If it's a tie, you cannot win the final title for the challenger, right? That's the rule. Okay. Yeah. In the real world, there is some rule. Okay. Yeah. But here, for us, so we just set some simple rule that can help us resolve the tie case. Yeah. Tiebreaker. So there is a tiebreaker rule. Okay. There is a tiebreaker rule there. Okay. Yeah. So here, let's only consider winner loser. Yeah. All right. Yeah. Here, okay, this statement. So the winner cannot be eliminated, right? Yeah. So this rule tells us only loser can be eliminated. The winner cannot be eliminated. Okay? Otherwise, it's ridiculous, right? Yeah. One player wins the game, but got eliminated. Yeah. Okay? Yeah. All right. So each comparison can only eliminate one element, not two. Is it possible zero? Is it possible zero? Because the loser has to be eliminated, right? The loser has to be eliminated. But here, the real world situation is a little more complicated than this. A real world situation, a little complicated than this. The real situation is this. All right. because we cover all the possible algorithms, right? Yeah. Including some algorithms are bad algorithms. Some algorithms, bad algorithms. Bad algorithms means it can do redundant comparison. Bad algorithms, because it's possible, if your algorithm is bad, you may do some unnecessary comparison, right? Yeah. But when you do unnecessary comparison, you don't get any useful information. Because that comparison is redundant. You pick a winner already, that one, yeah, we know, existing, yeah. The question, yeah, so here, yeah. Because if we enforce elimination, then because that player is eliminated, then it's gone, then we do not have a redundant, right? Yeah. Only you do not eliminate. If you do not eliminate a loser, then you may do redundant comparison. But if you eliminate the loser immediately, then you won't have redundancy, right? Yeah. So here, let's do some clarification. Yeah. So here, elimination. Why the elimination is good? Elimination, as soon as you know one player is a loser, you eliminate that player forever. Okay? Yeah. In that way, you won't waste any resource on a player already it's a loser. Okay? Yeah. But if you keep it, all right, if you do not eliminate that, you already know it's a loser, you still keep it, then you may do redundant comparison, right? Because that loser still, there is a possibility you do some useless comparisons. Okay? Yeah. So here, later we will make this method elimination method. Later, we will summarize the method we are using here is the elimination method. The main point of the elimination method, as soon as you know one element is not qualified for some criteria, yeah, so we have some, rule criteria, if it's not satisfied, not qualified for our final goal, we should eliminate it immediately. That's the elimination method. Yeah. Otherwise, if you do not do that elimination immediately, then later you will see you may apply redundant comparisons on that loser, on that, irrelevant. That element is irrelevant already. Okay? You still waste your comparisons on the irrelevant elements. Yeah. All right, let's continue. So we will reach our destination soon. Yeah, here. Yeah. So here I say eliminate at the most one element. So here consider the redundancy. Yeah. If we can remove the redundancy, then we can take away this at the most. Yeah. Yeah. Because if you have redundancy, you make an unnecessary comparison, then you do not eliminate any new player. But if we enforce strict elimination, then we won't have this redundancy. Okay? Yeah. So then, one comparison eliminates exactly one player. Okay? Yeah. All right, let's keep going. Yeah. So we will be there. Yeah. All right. At the end, because in order to get a final winner, we need to eliminate n-1 elements, right? We need to eliminate n-1 elements. But for the n-1 elements, you need at least n-1 comparisons, right? Because one comparison, you can only eliminate one. But now you need to cover n-1 elements. You need to consume at least n-1 comparisons, right? Could be more. If it's more, that's redundant, right? Yeah. Because you do some unnecessary work. So it could be more, but cannot be less. Cannot be fewer than n-1, right? Because if fewer than n-1, you cannot eliminate n-1 players. That's the final argument. Okay? Yeah. So one comparison, you can only eliminate one player. That's the common property for all the algorithms, right? Even unknown. So one comparison, you can only eliminate one element. But your goal, you need to eliminate n minus 1 elements. So you need at least n minus 1 comparisons. That's the argument, final argument. Okay? So after, this set of arguments, our final conclusion, this algorithm is optimal. Okay? Yeah. 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 So do you feel convincing? Do you feel convincing? Yeah. All right? Yeah. Okay? Yeah. Yeah. So we complete this question. All right. Yeah. But here, just let you know, this finding the minimum, this question is simple. The result, n minus 1 comparisons. And you also know it's optimal. Okay? All right. So this result, at this point, I'll let you know, we will apply this result many, many times in our later exercise questions. Okay? It will appear many times, this result. Okay? Although simple, yeah, but many different places you will use this result. Okay? All right? Next, D.2. Let's apply this result. This time we solve a new problem. What's that problem? Finding maximum and minimum at the same time. Okay? So what do you mean at the same time? So you apply your algorithm, but after you apply your algorithm, you need to give me both maximum and minimum. Okay? That's the end result. You only apply your algorithm once to give me both maximum and minimum. Okay? So it's not like, suppose we have a selection algorithm. It's not like the first time you apply, you get a maximum. The second time you apply, you get a minimum. I don't ask you to do that. I only ask you apply the algorithm once to give me both maximum and minimum. Not twice. Okay? Not twice. So once, give me both maximum and minimum. That's the meaning of this question. Okay? All right. Let's work on it. Yeah. Yeah. All right. So now you understand the meaning. Yeah. Let's do some analysis. Yeah. Yeah. Suppose we have these n elements. Yeah. All right. This time, we need to review the elimination method that we used in D.1, elimination method. All right. Where certain elements do not satisfy the criteria, because after we do some comparisons, if we notice some element cannot be the maximum, we can take it out of the consideration for maximum, right? We can take it out of the consideration for maximum, but we still keep it for consideration of minimum, right? Yeah. But if an element is not qualified for the minimum, we can take it out of consideration for minimum, but we still keep it for consideration of maximum. Yeah, things like that. Okay? So here we need to, do something very careful regarding the elimination. Yeah. All right. So when certain elements do not satisfy the criteria, maximum or minimum criteria, just some, we can eliminate them from the consideration. Okay? Yeah. All right. Yeah. All right. Because after elimination, the data size is reduced, right? Yeah. The data size is reduced. You have fewer elements to be considered. So those elements to be considered, that's your current data size. That data size becomes smaller. The smaller the data size, do you feel it's easier to find the final solution? No. The data size becomes smaller, smaller, okay? Yeah. Easier. Yeah. All right. Yeah. Right. But here, let's introduce some simple notation. Yeah. So, when we do the work, yeah, we do not want to write a lot of words, right? Yeah. So we want to use some short, concise notations to represent some special meaning. Yeah. So here, let's use some notation for comparison. Yeah. Xi, comma xj, parenthesis. Yeah. That means we do a comparison between these two elements. Then, as a result, there is a winner and a loser, right? Yeah. So here, let's assume if the winner is xi, so we draw arrow. Yeah. Xi is the winner of the comparison result. Yeah. If we need, we use this simple notation. Okay. Yeah. If we need, yeah. All right, the winner. We know it's a winner. Yeah. But for the winner, yeah. So for the winner, yeah. So sometimes we need to clarify. Yeah. The winner. Do you mean the smaller value is the winner or the larger value is the winner, right? Sometimes we need to clarify. Yeah, but our intuition favors the larger one to be the winner, right? Our intuition. Yeah. Yeah. The smaller one to be the winner, it's like against our intuition, right? Yeah, a little bit, at least a little bit. Yeah. So sometimes we need to do adjustment. Yeah. But sometimes, we may like to choose the easier way. Okay? All right. Based on the requirement. Yeah. All right. Now let's look at the details of the data manipulation. Now we need to work on these n elements. Okay? Yeah. All right. Yeah. Let me see if I have enough time. Yeah. All right. I hope I have enough time to finish this one. All right. How do we organize our data for comparisons? Yeah. Data organization is very important. In our first chessboard question, we know data organization is important. Yeah. Here, we need to do some data organization. Yeah. All right. So what kind of data organization? We need to do grouping the data in pairs. Our data, these n elements, that's our data. But before we do comparison, let's do some simple grouping them in pairs. Okay? First pair, second pair, third pair, and so on. Okay? Yeah. If we do analogy in sports games, this kind of arrangement like tournament method, right? Yeah, people, frequently use the tournament method. Yeah, the players are grouped in pairs. Then they play each other. First round elimination, second round elimination, and so on. Right? Keep doing elimination. Then final winner. Yeah. So for this class, we will use the tournament method a lot. Okay. Yeah. So here. Introduce this tournament method. All right? Yeah. Yeah. Group them in pairs. Okay? Yeah. But when you group them in pairs, there is a possibility, because if you have all the number of players, there is one player you cannot put it in any pairs, right? Yeah. That player, in the current round, idle, right? That player is lucky, moves to the next round automatically, right? Yeah. So we have that situation. Yeah. So, all right. So there are two cases. We need to consider number of elements could be even or odd. Two cases we need to work. Which case you want to work first in this situation? Which case you want to work first? Why odd? Yeah. Curious said he wants to work on the odd case. Yeah. How about other students? Even case or odd case you want to work? Why odd? Or harder or easier? Yeah, harder. So you want to work on harder cases first? You feel, yeah, you work on harder cases first, easier cases the last? Yeah. All right. When you have a set of math questions, do you want to work on the hardest first? If you work on the hardest, if you get stuck, if you couldn't solve the hardest one, then when you finish the 2 hours period, you get 0 points, right? Because you work on the hardest first, and you couldn't get it, okay? Yeah. If you work on the easiest, you can get some points, right? So based on your real world experience, when you have a sequence of problems, do you want to start from the easiest problem first or hardest problem first? Okay? So based on your experience, your intuition, yeah. So people call it the golden rule. Always work on the easiest problem. That's the golden rule. Okay? Yeah. Don't make your life harder. When you work on the hardest problem first, you make your life harder. Okay? You will suffer from the consequence. The golden rule, from the easiest first, gradually increase the difficulty levels, and when you move to the harder levels, you already build up your experience. Because when you start from the easiest problems, at the same time you build up your experience. So you have a lot of experience. When you move to the final step, the hardest, you have a lot of experience, so you can do better. But when you work on the hardest, you don't have any experience, right? But you need to work on the hardest. Okay? So that's why people call it golden rule. Okay? Always work on the easiest. And build it up. And, get experienced. It's like a preparation. So working on easiest cases, so you are doing preparations for the last one, the final, the hardest one. You have good preparation, okay? Yeah. All right, so that's the important. Yeah. And we will use this as our problem-solving strategy. That's our problem-solving strategy, okay? All right, here, yeah, even case easier. Let's work on the even case. Then, after you finish even case, you have the experience from even case, okay? So you do not start from scratch for the odd case. What do you need to do? You only do small modification to get odd case. Because the difference is not big, right? Even our difference is so small. So you only need to spend a little extra effort to cover that small difference. Then you're done. That's the main point. Okay, all right, yeah. Let's start. Yeah. All right, so work on the simplest case. Yeah, so here, okay. Let's work on the even case first. Now, let me check the time. Yeah. Let me see. Right, more than 5 minutes. At least more than 5 minutes, yeah, because I want to complete it. Right. Yeah. Actually, it's not that hard. So I think I can complete it. Yeah. After we did so much comparisons mentally, I think we are ready. Yeah. Yeah. So now you have some good training in elimination method. So you have good training in elimination method. Okay. Yeah. All right. So now we're pretty much ready to apply the elimination method and the tournament. So two methods. We need to use two methods here. One, tournament method. Second, elimination method. Then you can enjoy the result. All right. Oh, before we start, there is one important step. Let me use 2 minutes. We need to do that step. Because we just learned finding the minimum, we need A-1 comparisons. Let us use our first try. So here, let's do first try. Do you want to apply our previous solution, finding the minimum, to find the minimum first? Kiri, do you want to apply that existing algorithm to find the minimum first? You want, right? Yeah. Most people want to do that, right? All right, first, let's do that. Finding the minimum, let's say for the minimum, we apply existing algorithm. We need an N-1 comparison, right? All right. After that, because the minimum is known after N-1 comparison, when we find the maximum, do we need to consider that minimum? We already find the minimum. Okay. Here, let's assume more than one element, right? Yeah. If one element, that's trivial, so we don't look at it. Okay. More than one element, the minimum has no chance to be the maximum. Oh, let me do another simplification. Let's assume these n elements are distinct, because you may ask me, how about some equal case, right? Yeah. Let's assume distinct elements. Right? Just make our life easier, right? Yeah. So it's okay. Make our life easier. All right. Then distinct. The minimum cannot be the maximum, right? Is it safe to eliminate this minimum from the consideration for the maximum? It's safe, right? Yeah. Let's do that elimination. Then, to find the maximum, next round, how many comparisons do we need? Next round, N-1. 2, correct, 2. For the max, we need N-2 comparisons. All right, total 2N-3 comparisons. All right, 2N-3. All right, this is our first try. Okay, first try. 2N-1 plus 2, 3. All right, 1 plus 2, 3. Yeah. Yeah. All right. We have to be. I only have 3 minutes. Oh, okay. I only have 3 minutes. Okay. All right. But my discussion, I think, more than I cannot finish in 3 minutes. Yeah. All right. So let me just say something. Yeah. So we leave the remaining part next time. But I just say something. Yeah. But we have not completed. Yeah. All right. First. The first try will not give us the best solution. Here, let me explain why. Then we just finish. All right. The reason this first try, we didn't use all the known information. We didn't use all the known information. We wasted some useful information in the first try. Why is that? Think about it. when you do the second round, we do first round and second round, right? Second round for the max, you didn't use any information collected from the first round, right? First round, you did n-1 comparisons, so you should have a lot of information. No, but you throw away the known information. You start from scratch, although you eliminate one element, but that's not enough because you have a lot of known information you didn't use in the second comparison. So you waste a lot of information. So that's why this solution cannot be the best solution. We can save more. We can save more. Okay? All right, so let me stop right here. So in the next class, let's